Okay, you should have at lecture 44 notes. All right, we're going to do hypothesis testing for a mean examples, part 1. All right, I'm going to do a problem here, and it's going to have a pretty formal way of going through it, but it's still going to harken back to all the intuition I hope we have built up. And after I do that, we're going to come back and do it one more time in a slightly more streamlined version. And I think then the streamlined version will be really clear to you. And that will be the way that we want to do most problems, okay? And then we'll actually do it a related problem after that. First, we're going to use z-scores, and then we're going to do this related problem at the end using t-scores, and I'll explain all that as we get to it. All right, so lecture 44, hypothesis testing for mean examples, part 1. Example 1, and this is taken from was lecture 41, I think. Suppose a certain type of tomato plant gives a mean yield of 12 pounds of tomatoes per plant with a standard deviation of sigma equal 3 pounds. We introduce a new fertilizer to a random sample of n equal 36 of these plants and find the sample mean yield is y bar equals 13.6 pounds. Assume the standard deviation stays the same at 3 pounds. And that's the thing that's a little bit unrealistic, simply to say, well, the mean maybe is changing because of this new fertilizer, but the standard deviation, we're just going to say, isn't. That's probably not a safe assumption to make, but we're going to make it here just to simplify things a little bit this first time around. All right, so we're going to assume the standard deviation stays the same. Test at the alpha equal 5% significance level the claim that the new fertilizer increases the average yield per plant. All right, so I say, hey, first we check to see that the conditions are right for us to proceed. Basically, all that follows is based on the assumption that the sample mean random variable can be assumed to be normal. And we make this assumption with confidence because our sample size is n equal 36, and we have our little rule of thumb that says, hey, that's bigger than or equal to 30. So that tells me that enough of the conclusion of the central limit theorem is kicking in, so I can assume that the sample mean would be normally distributed. All right, and so with that in mind, if y is the yield, y for yield, in pounds of tomatoes from a randomly chosen plant, what we're interested in is this random variable y bar, right? If I were to create this whole new population with the fertilizer and take a sample of size 36 here and a sample of size 36 there, and all these samples of size 36, and for each one computed the sample mean, I would have a new set of numbers, y bar, the sample mean, and we're saying that that's normally distributed. And in fact, what do I say here? It's under the assumption that the null hypothesis is true, the sample mean y bar will be normal. In fact, what I say is y bar will be normal with the old mean. That's under assuming that the null hypothesis is true, which we haven't even gotten to yet, but we know that the null hypothesis is that that we stay at the old mean, which is 12 pounds. I'll write that in a second. But the standard deviation will be sigma over the square root of n. In other words, we're going to be assuming here that the sample mean is mu naught was the mean of 12, so it's normal with mean 12, and 3 over the square root of 36, that's 3 over 6, so it's 1/2. So really what we have is that y bar will be normal with mean 12 and standard deviation 3 over 6 or 1/2, right? 0.5 if you like. Okay, now I want to make sure we see the picture there. So what we're really saying here is the y bar curve, and I want you to have this down, is centered at 12, and it's going out here like that, right? Okay, now what are we doing? We are having an actual sample mean of 13.6, and the question is that an unusual value enough for us to think, unusually high enough for us to think that, well, really this mean is wrong, we need to shift over. And let's see. So what I do is I stick in here, what did I say here? I didn't do it. I guess I guess the next question I want to ask, we're going to come back and put some more on this curve, but the next question I ask is, what are the null and alternative hypotheses? And we've already seen that the null is that mu is 12, and the alternative is that mu will be greater than 12, that we need to shift the curve over, right? Okay, I say here then, our value of the sample mean is 13.6 pounds. Is this unusual or not? Is it unusually high or not? So let me just stick it right here. It's maybe sort of exaggerated, you know, how far out, but just put it there. It's easy for me to draw around it if I put it right there. So this is my sample mean. If you remember, if the random variable we write as a capital letter, and the particular value of it we usually write as a lowercase. So I have a lowercase y bar, and that's my 13.6 pounds. Is that so unusually high that we are going to reject the idea that the mean is 12 and think that it's actually bigger? And to know that, we must figure out what unusually high means, and to do that, we will use the significance level, which I tell you here, it's 5%. All right, so what I want to do is I want to find the cutoff yield for the significance level of 5%. So I say here, let's start with the z-score. So remember, this is how we find cutoff values that have a certain tail probability. We start with the z-score and get the z-value that has that tail probability. Then we convert back to what the actual random variable value is, or what the actual data value is. So we start with the z-score, and what we're looking for on the z-curve, then, this is the z-curve, we are looking for, here, the area is going to be the significance level alpha, which is 5%, and I hope you understand 5% means 5 per 100, 5 over 100, so it's 0.05, right? So I'll write it like that. Alpha is 0.05, and so what I'm actually looking for here is what we call the critical value, z sub 0.05, right? And what is that value? Well, I got to look in my table for area to the left being, well, what's it going to be? If all of the area is always 1 and I have 0.05 to the right, I want 0.95 to the left, correct? And if you go and look in your table, you're going to find that maybe your table, the closest you'll have, will give you a z of 1.64 or maybe 1.65. A lot of tables will actually pick that special value because it's such a significance level that's used so often. And there'll be maybe a little arrow that points out of the table and gives you this value to a greater number of decimal points. And if you do that, if your table does that, and probably it does, you'll see that it's 1.645. All right, that's the z-score. That has that much area to the right. What is the corresponding yield value for these tomato plants that has that much area to the right? So I say over here, going off to the right, then I say, now get the cutoff weight itself, or cutoff yield. Cut-off weight, or yield. And yeah, that fit, okay. So I'm back to drawing this curve, and you know what? Well, I guess I will go ahead and redraw it here, since that's kind of the way I have it. So here's my 12, all right, and here's my 13.6, what I actually got. Now, how do you get it? I don't write it there, but I want to write it out for you here, and that is, we've done this before. I say to get the cutoff weight, I hope you remember what you do is you do the mean, and this is, I'm going to have to change my marker color here because it's kind of dying on me. You want to do the mean, that's better, mean weight plus z-score, I'm running out of room here, but times standard deviation, right? So it's a z-score times standard deviation, and you add that to the mean weight. So it is 12 is what we're assuming the mean is, plus the z-score we found to be 1.645. And what's the standard deviation? For y bar, this is y bar again, right? The standard deviation is right there. It's 1/2. So I take it times 1/2 or 0.5. And what you end up with is about 12.8, I guess. So it's around 12.8. Okay, so you'd put that here, and you'd put it back over here. This is the cutoff weight, right? This is the cutoff weight. So that's saying that all this green area here, that's my tail probability of 0.05, right? Well, I can now look at this and say that, oh, my value is more extreme than my cutoff weight. So my conclusion here at the top of the next page is, so we reject H naught, correct? H naught was that we think the mean is 12. H1 is that we think it's greater than 12. The value I got for the sample mean pushed past what our cutoff weight is for what we're considering unusual for Y bar. So that indicates that I'm probably wrong. And at the alpha equal 5% significance level, I'm probably wrong here, and I should move my mean over somewhat. It's a bigger value. So the final conclusion is the following. All right, you need to have this down. At the alpha equals 0.05, or you can say 5% significance level, and I'm going to abbreviate significance. Please write it out. I'm just abbreviating because I don't want to run out of room here. There is sufficient evidence to reject what H naught is saying, and we must say what it is saying in the context of this particular problem. There is sufficient evidence to reject that the mean yield with this fertilizer will be 12 pounds per plant. Again, per plant is what you want to write there. I'm just abbreviating because I'm going around out of room. All right. So it appears that the yield will be greater, right? We can add that. It appears that the yield will be greater. All right, let me tell you that everything that we are doing all through here is to get us to here. This is where we add to whatever people want to understand about the situation. This is the statement that says so. We have sufficient evidence at this 5% cutoff for unusualness level to reject the claim that the mean yield with this fertilizer will be 12 pounds. We have reason to think it's going to be greater. We don't want to say how great, we don't know, right? But we think that the curve should shift to the right. So we do believe that the fertilizer is doing something. Okay. And like I said, this is about the second or third time I've essentially worked through this problem, but it's the first time I've used more formally some of these ideas. Okay, if you'll bear with me, I want to do it one more time, but even in a more streamlined fashion. Okay, so I think that's what I say here. The above is a perfectly reasonable way to do this problem, but we're going to redo it in a more streamlined fashion and not worry so much about the curve for Y bar itself. We're just going to be able to use the Z curve, and so things go a little bit faster because we will, instead of converting everything to be over here, we'll convert everything to be over here, and we'll find the Z score of this 13.6, and it'll sit over here, and we'll be able to compare the Z score of the sample mean with the Z score of the cutoff value rather than do the comparison over here in this curve, and it'll streamline things a little bit. Okay, and it'll be kind of the way we want to do things. All right, so let's see, you can read. So I have example 1 again, and I think it's all the same. It's exactly the same. So you can reread again if you need to, but we will kind of zip through this, I think, a little faster now. Okay, first it says, We note, so step 0 I'm calling it, we note that n is, the sample size is equal to 36 is greater than or equal to 30, so we're confident to proceed. The central limit theorem should allow us to have decent results. So, number 1, null and alternative hypotheses. We already know. H naught is that the mean is 12 pounds per plant. We should probably say pounds per plant. Doesn't hurt to lay it out in detail right away so you keep the context going, right? So that you're, in the end, you're thinking about the real world situation and not just number crunching. Mu is greater than 12 is the alternative hypothesis, and I'm not going to stick it in pounds per plant here because I want to say something here. If I'm thinking that the population mean is actually bigger, this is what we call a right-tailed test, which should make sense to you because we already talked about that. So it's good to have that in mind so I know when I draw the picture, I'm going to be looking off to the right. All right, step 2, this was step 1, yeah, step 2, it says construct, since we're assuming sigma remains at 3 pounds, we know that we will use z-scores. So we're going to construct the z-curve showing the critical value z.05 and the rejection region. So I'm just going to construct the z-curve, and I know that alpha equals 5%, so that's my alpha, and this is z.05, which we already found in 1.645. Okay, and again, if you don't remember how to do this, that's from way back, right? You can dig back in your notes and see how to find z-scores for given areas. But, I did it very quickly when I did the other version. We got to find 95% to the right. You got to go in the table and look for it. And this is one of those values that it had it kind of off to the side or in a lot of tables where you can get it, closer to the actual value, the exact value. All right, so anyway, I got that. And then I say, okay, we compute the test statistic. I didn't do that last time because the test statistic is what we are calling the z-score of our value of the sample mean. So we compute the z-score under the assumption that H naught is true. That is, assuming that the population mean, mu, is still 12 pounds. So in step 3, the z-score of our sample mean we found, what we do is we take whatever that value is, and this is how I did it, yeah. We take whatever that value is, we subtract what we believe the mean to be under the assumption of the null hypothesis, and we divide by the standard deviation, which is s over the square root of n, correct? And that is, oh no, sorry, not s, we're not there yet. We're going to do that next time. It's sigma. We have sigma is 3, so we still have sigma, so it's sigma over the square root of n. So this becomes, plug in the numbers, 13.6 minus 12 divided by sigma, which we say is still 3 over the square root of 36. And we do all that and we get 3.2, right? We get 3.2. And I say, go ahead, assume that okay, at this point, I want to do this. I want to say, here is 3.2. That's my z-score, right? For the sample mean, let's plug that in up here. That's going to be, change my color again a little bit here. That's going to be, out here somewhere, right? Isn't it? Because there's 1.645. So out here somewhere is 3.2. So it's clear that it is out in the rejection region. I forgot to say, this is the rejection region, isn't it? Right here. Everything beyond the z-score of the cutoff value, everything beyond the critical value. This is the rejection region out here. This is where if the test statistic falls, we reject the null hypothesis. So obviously, we're going to reject the null hypothesis, right? So I say that. But before we get there, I want to say something to you. And I want to stress the idea that we, as I've said before, we have 2 ways to do this. I look at the test statistic, see how far out it is compared to the critical value. If it's farther out, I'm going to reject. But the other way I can do it is I can compare the tail probabilities. What's the tail probability of the test statistic versus the tail probability of the critical value? The tail probability of the critical value we know is the significance level, which here is 5%. What is the p-value? The p-value, if you remember, it's the tail probability, tail probability of the test statistic. So I go in my table and I look up, you should be able to do this. I go find 3.2. I'm not getting out the tables and putting them up here and going through that, because you should be able to do that now. I'm just telling you, you go in, find 3.2 in z-scores, and you will find that it has 0.9993 area to the left. So the p-value is 1 minus 0.9993, so it's 0.0007. So certainly the p-value is less than alpha, which again means tail probability is less for the test statistic. We're going to reject. But it's just another way of saying the same thing, right? Because now what I'm saying is this area out here, which I can, hardly write it. This area out here is 0.0007. It is less than the significance level, which is 0.05, so we're going to reject. But also the test statistic lies farther out, just seeing the test statistic compared to the critical value, so we reject as well. So once again, doing a p-value versus alpha comparison is doing the same thing as a test statistic versus critical value comparison. Both will tell you that in this case, we want to reject H naught. So I end with, I'll let you fill it out. It says, do we reject or fail to reject? Well, we know that we reject because of this. And then what's our final conclusion? You fill it in. It's the same as before. I'm not going to rewrite it all. It's the same thing that I have down here, partially erased. But please fill it back in. You need to work with these conclusions. They are the whole story. All right? They are the whole story. And so you need to be very good at writing them down. Okay. Now, let's revisit, and this time, so what do I say? I say, well, okay, so that's the basic outline. So this is how you would do the problem. Let's do a very, very similar problem, but this time we're going to assume that since the mean may change, the population mean, the population standard deviation may also change, and we can't just assume that it's sigma equal 3, right? We can't use that sigma. Okay, so that's going to mean we're going to have to use t-scores instead of z-scores. So let me blast through that. It's going to be, very quick, but it's going to use t-scores. Okay, so let me read here. Suppose a certain type of tomato plant gives a yield of 12 pounds per plant. Standard deviation is sigma equal 3. We introduce a new fertilizer to a random sample of n equal 36 of these plants and find the sample mean is 13.6 pounds. So, we have, so this I call it example 1 prime. Okay, so again, we have that y bar is 13.6 pounds, but this time, though you happen to know that the standard deviation of the previous population was 3, that's really of no use. We don't know that we can trust it anymore. We compute the sample standard deviation to be 4.5 pounds. And this is like the problem I introduced a few lectures ago, but I changed the numbers a little bit because I wanted to make things come out a little bit different. Okay, so we have this with this new fertilizer. And I want to test at the alpha equal 1% significant level, which is at the 0.01. That means the critical value goes farther out, right? So it is harder to reject the null hypothesis. You have to have a more extreme value to get out farther, right? All right, we're into the rejection region. Okay, so anyway, you can read that parenthetical paragraph there, but step 0, n equal 36, greater than or equal to 30, so we can proceed. Step 1, null and alternative hypotheses. Mu is 12. Mu is greater than 12. That doesn't change. Step 2 says, okay, we're going to do the same thing that we did over here, only we're going to do it with t-scores, right? So what do I say? We know that the new population standard deviation, we do not know it, so our test statistic will not be a z-score, it'll be a t-score. If the degrees of freedom are 35, because it's 36 minus 1, or we want the critical value of O. let's see, t.01. I have a typo here I'll have to fix. We want the critical value of t sub 0.01, like over here it was z.05. We want t sub 0.01. So let me show that, and let me show the rejection region. So, I have what's basically still my bell curve, only this is the t random variable. This is t, where degrees of freedom equal 35, right? 36 minus 1. So somewhere out here is t sub 0.01, and that's going to be my alpha is 0.01. And I looked this up in a table, and I get 2.438. Okay. All right, finally, what's the t-score then? Test statistic. And that is the t-score, this time not the z-score. So it will be the value I have for y bar minus mu naught, which is assuming, that h naught is still true, divided by, now it's s over the square root of n. All right, so I have y bar, it was 13.6. Mu naught was 12, divided by s is 4.5, and this is still the square root of 36. And if you work all that out, you get 2.13 roughly, I think is maybe repeating, 2.133333. Okay, well notice then, if my critical value is 2.438, 2.133 is somewhere in there, it's not in the rejection region. All right, it's not in the rejection region. And so we know that we're going to fail to reject H naught. But let's also think about p-values versus significance level, because I want to, again, stress that way of thinking. So I say, what about the p-value? Well, we have a little bit of a problem in actually calculating it, right? And I mentioned this in an earlier lecture. I have this t-score, but if I go look in most t-tables, it's just giving me, because you have to have all the different degrees of freedom, it's just giving me a few t-scores for various areas in the tail, right? It's pretty unlikely that if I go to the, degree of freedom 35 line, this t-score will happen to be in it. And in fact, if you go and look for most tails, it isn't. For most tables, it isn't. What I found was that this t-score is between the two t-scores. This is, let me just say that this is between, what was it, 2.438, this one up here, right, and 2.030. Okay, so this corresponds to a tail probability of 0.01, and this corresponds to a tail probability of 0.025. Okay, so I can say, the p-value, the tail probability for 2.1333 whatever, is between 0.01 and 0.025. I can't, from the table, figure it out exactly. So I think I once said, well, you can't compare then with significance, but I can compare. I just can't give you the exact value. I shouldn't have said that I can't compare. I just can't tell you the exact number here and compare it up here. But I know it's between these numbers, so it's bigger. So it's bigger than 0.01, which is alpha. So again, p-value bigger than alpha, so we reject. So in both ways, we see and I guess I have that down there. That's actually step 4, right? Step 4 is, so we reject H naught. We fail to reject H naught, right? It does not lie in the rejection region, or the p-value is, though I can't figure it out exactly, I can see that it's bigger than the significance level, so we need to reject, fail to reject H naught. I got to say that right. So that's step 4, right? Step 4. Fail to reject H naught, all right? How do we write the final conclusion then? I think I'm going to, again, switch. All right, so the way I would say it, the way that is pretty common to say it is, at the alpha equal 1% significance level, there is insufficient evidence to reject the null hypothesis, correct? But what is the null hypothesis? The null hypothesis is that the mean yield per plant is still 12 pounds. So there is insufficient evidence to reject the claim that the mean yield per plant is 12 pounds. Now study that for a second. Do you see that it's just easy to get it wrong? Because I am not going to say, we've talked about this over and over, I'm not going to say, we failed to reject means we accept H naught. We believe H naught to be true. I'm not saying, no, the mean didn't change. I'm not saying that. I'm saying we don't have a strong enough evidence to believe that it changed. We can't really say very strongly at this significance level that we believe that it changed. So it is insufficient evidence to reject H naught, which is that the mean yield per plant is 12 pounds, all right? And you could add, we don't have strong reason at this significance level for believing that the yield increased. That's really what we're saying. And I add, let's see, I guess I want to point out here, then at the very bottom, I want to say, think about this. We always, in the final conclusion, we either reject H naught, and when we reject H naught, we start with the statement, or can start with the statement, there is sufficient evidence to reject H naught. If we fail to reject, we start with there isn't sufficient evidence, so there is insufficient evidence. Whoops, yikes. Hope we're still there. There is insufficient evidence to reject the claim that is in H naught. If you remember that your final conclusion always refers to H naught, I'm rejecting H naught, I have enough evidence to, or I'm failing to reject H naught, I don't have enough evidence to reject H naught. If you keep that in mind, that will help you get it straight. And always when you reject or fail to reject H naught, you don't simply say H naught or H sub 0 or the null hypothesis. You say what it is in the context of the problem. In this case, that the mean is 12 pounds per plant. Okay, we will stop here. We'll do a couple more examples next time, and we'll go very fast through them.